Welcome to the fourth lecture of module 2. Earlier we have done in module 2 two lectures on the sol-gel method of synthesis, and the last lecture, which was the lecture 3 of synthetic methodologies, was the beginning of the topic of microemulsions and microemulsions based synthesis of nanostructured materials. Today is the second lecture, which is a continuation of the synthesis using microemulsions of nanostructures, and basically today we will be studying about how we use microemulsion technique for the synthesis of different sizes and shapes of various variety of nanostructured materials. In a typical synthesis of nanostructures, first you have the nucleation stage. So, small embryonic nuclei form, and then these nuclei grow to form the nanocrystals. So, there are two major steps in any crystallization. You have first nucleation, and then these nuclei grow to form the nanocrystals or nanoparticles, and the important thing is how to control the size of the nanoparticles depends how you control the growth of these nanoparticles. So, to understand the methodology of controlling the size of nanoparticles, we have to understand the thermodynamics and kinetics of these two processes, which is nucleation and growth of these nanocrystalline materials. So, one of the mechanisms by which these nanocrystallines form and grow is by what is called the Ostwald ripening method. In the Ostwald ripening method, it is basically considered to be a thermodynamically driven spontaneous process. In this process, large particles grow at the expense of small particles. These large particles are energetically more favored, and hence the small particles in the vast number of nuclei which form change into or grow into these large sized particles. So, they attach themselves to the larger sized particles, making them even larger, and by this they reduce the surface energy, because smaller sized particles have more surface energy, and so the larger sized particles are energetically more favored, and this is the thermodynamically driven process. Spontaneously, whenever there is a growth, it happens through the Ostwald ripening process, since it is what is defined by thermodynamics, and energetically you will have growth of larger particles and less number of smaller particles will stay till you reach equilibrium. So, if you look at the formation of a large number of nuclei of small size, as time grows, the number of particles with a particular size will which is larger than the initial size of the nuclei will become larger. There will be more particles with larger size, and hence the distribution of particle size will become very narrow, and you will have most of the particles at one size, which is a reasonably large size of particle. So, initially you will have particles of very small size, and then you will have particles of various sizes, and at equilibrium you will have a majority number of particles at one particular size, which is a large size, and the size distribution will become very narrow as time goes on. And this is the Ostwald ripening process, and as I said earlier, this is the thermodynamically driven process, and it will occur spontaneously in any system unless you give some external input, external driving forces, which may be in the order of salts or other chemicals or some electric field or magnetic field, then you can go to a process which is kinetically stable and not the thermodynamically driven process like which is guided here through the Ostwald ripening process. So, this is an example of hollow titanium dioxide which is forming through the Ostwald ripening process. So, you see solid TiO2 spheres. Initially there are large number, numerous small crystallites which you can see here in this model. As the time goes on, the inner cores, which are smaller spheres, they have higher curvature, higher surface energies, and they dissolve and you get more larger particles towards the edge. So, the core particles which have higher surface energy compared to the particles on the surface on the exterior of this large group of particles. So, that will grow, and inside the particles which have more curvature and higher surface energy will be lost, and this is a model of what is happening in TiO2, how hollow TiO2 is forming, and these are real pictures where you see that the outer part of these large agglomerate of particles is becoming darker and the interior is becoming lighter. This is the hollowing effect which you observe because of Ostwald ripening at longer reaction time. And this we have also observed in many other systems, for example, in silica particles which we have made using microemulsions. You can see these pores, and with time you can increase the size of these pores, and this is typically what you see in the last case as we discussed in TiO2, where Ostwald ripening will increase these pores and will lead to more dense outer structures. The other alternative to Ostwald ripening is what is called the digestive ripening. This is not the thermodynamically driven process. This is against the thermodynamically driven process, where large particles break apart and small particles increase in size. So, this is just the opposite of Ostwald ripening. In Ostwald ripening, you have small particles getting removed from the system and the larger particles growing. In this case, large particles break apart and small particles increase in size. And why does this happen? This is due to some external influences. For example, if you add some thiols, some long hydrocarbon chain thiols which have 8 carbons to 16 carbons, these kind of thiol molecules bring about this kind of digestive ripening through some electrostatic interactions. And these kind of materials or these kind of molecules are called digestive ripening agents, which help in this process, where instead of having large and small particles, the larger particles break to become uniform small sized particles, as seen here in this particular case, which is published in these 2 journals, and you get a very uniform homogeneous distribution of particles of very small size through this digestive ripening process. This process is not thermodynamically driven, it is kinetically driven, and this process is helped by the presence of molecules like thiols, which act as digestive ripening agents. And this kind of work has been shown in the literature by Klabunde et al., and these are some of the publications where details of the digestive ripening process, the kinetically driven process is explained in detail. Now, typically how you synthesize nanostructured materials. So, we will study how we synthesize using two microemulsions by which we get metal oxalates or metal carboxylates and then generate binary metal oxide nanoparticles. In our earlier lecture, we discussed that whenever we have to make nanomaterials using microemulsions, we start with 2 or 3 or 4 microemulsions, depending on whether we want a binary oxide or binary chloride or ternary material or quaternary material. Depending on that, the number of microemulsions that you take increases. So, in this case, since you have we will be taking binary metal oxides, we want to synthesize binary metal oxides, that means one metal and one oxide oxygen species. So, you need 2 microemulsions to start with. In one microemulsion, you will have your metal ion, say cobalt or nickel or iron, and in the other microemulsion you will have the oxalate or succinate or any carboxylate by which you will precipitate the metal carboxylate. And then using this metal oxalate or carboxylate, you slowly decompose it to get binary metal oxide nanoparticles. So, these nanoparticles we can control using the microemulsions. The size and shape of these nanoparticles can be used by effectively choosing the various parameters which govern these microemulsions. So, what are these parameters? These parameters are like the solvent, what is the non-aqueous medium. For example, it can be benzene, it can be toluene, it can be heptane. What is the surfactant? As we discussed in the previous lecture, you can have surfactants like cationic surfactant, you can have an anionic surfactant, you can have surfactants with one tail, that is a hydrocarbon chain, or 2 chains or 3 chains. So, you can vary the nature of the surfactant, you can vary the head group, what is the charge on the head group, whether it is positive or negative. Then you can change the W naught parameter, which is the water to surfactant ratio. That will also control the type the size of the microemulsion that is formed. The nature of the ligand is important, what kind of ligand you want to attach to the metal. For example, is it a carbonate ligand, is it a oxalate ligand or succinate, that will affect the dynamics during the mixing of the microemulsions. There are effects of the ligand, the oxidation state of the metal ion may be important because it depends on the solubility product of the metal ion with the ligand, and that will vary whether it is iron +2 or iron +3. You will have to worry about what is your starting reagent, whether you are taking ferrous chlorides or ferrous nitrate. Then variation in water surfactant ratio we already discussed will affect. So, all these parameters have a role to play in the type of microemulsions that you get and can be varied to get a large variety of metal oxalates or carboxylates, and it can be extended to other systems like metal sulfides, metal selenides, metal phosphates. So, here we will discuss first the synthesis of metal oxalates using 2 microemulsions, and then we can enhance this. Instead of from 2 microemulsions, we can take 3 microemulsions and get ternary phases, and then get ternary oxide materials like barium titanate, strontium titanate, where you have 2 metals and 1 oxygen. So, it is a ternary system. This is also a ternary system. So, starting first from a binary 2 microemulsion system, we can discuss how we can go to 3 microemulsion systems and get ternary oxide phases, which are very important for several applications. So, this is one example where we have taken a cationic surfactant, and when we take a cationic surfactant, what we observe is that when the metal precipitates with the oxalate, then it might form this kind of chains, and we find that in our microscopic studies, and we can explain why metal oxalate nanostructures form this kind of linear chains, because it can be explained these oxygen ions which have a negatively charged will attract the polar head group, which is positive in case of a C tab, which is the cationic surfactant. So, the cationic surfactant will be aligned along these surfaces, and hence growth will be more amenable along this axis, but not along this axis. This is one of the mechanisms that has been proposed for the formation of anisotropic nanostructures in metal carboxylates, especially when you take cationic surfactants. And the reason, as we said, is because the surface of these rods will be negatively charged, and that can be measured using a technique which is called zeta potential measurements, and you can measure the surface of these rods, and since they are negative, they will attract the positive head group of the cationic surfactant like C tab, and the growth will be along this direction, and you will end up with nanorods of these metal oxalates. If you do not use surfactants, that means if you do not use microemulsion, then you will not get rods, and this is, you can take any type of metal like iron, nickel, cobalt, zinc, manganese, all of them form metal oxalates, and they form rod like structures because of this positive or cationic surfactants which make them aligned along these two sides and allow for growth of the rod along one dimension. Now, there are generally the mechanisms by which other rod formation take place is through what is called assembly of nanoparticles to form rods, nanorods. So, here if you have, for example, zinc acetate particles, and inside this is a polymer like PVP. Now, PVP plays a very important role here for formation of the nanorods. So, in this case, if you have these kind of zinc acetate particles along with the polymer and you dry this at 383 Kelvin, this is an optimal temperature for this polymer PVP, then you see these particles becoming larger from here, and if you heat for a higher temperature for some more time, then you will see this rod like growth. On top of the surface, you see these particles are aligning themselves, they are assembling on the initial rod which forms, and as time goes on at that temperature, these particles coalesce on these rods and you get a larger nanorod. So, this is one of the methodologies how you get nanorods from nanoparticles by self assembly during the drying up of the polymer along with the metal ion solution. So, this is a very well known technique now by which nanorod formation can be explained. Now, the other way that this rod formation is explained is that you have these nanoparticles. This is called the population balance model of nanorod formation, is that you have these nanoparticles which are colliding and they form this kind of dimers, and then further collision to give you trimers, and then it continues to form tetramer and pentamer, etc. Now, when they can form 2 pentamers may collide and form a 10 or decamer, and this continues, and then these particles start coalescing. So, these are like a pearl string, each aligned next to each other in a linear fashion, and after some time they coalesce, and as they are coalescing they form this neck formation is there, and finally, they give the nanorod. So, this kind of a linear pearl chain formation is happening through the oriented attachment of nanodots. So, these nanodots, whenever there is a trimer, one more nanodot can come and align itself here. So, this is called the oriented attachment mechanism, and this basically first there is a oriented attachment, and the second stage is the coalescence of the aligned nanoparticles to give the final nanorod. So, the oriented attachment of the particles and then coalescence together give you the mechanism for the rod formation in these systems. There is another reason for this oriented growth. If you have a permanent dipole moment, then many of these spherical, what we consider spherical nanocrystalline particles are actually not spherical, they are quasi spherical. That means, there is some distortion of the sphere, and that distortion or the quasi spherical nature of these crystalline nanodots, that will result in a dipole moment along the polar faces of these nanodots. Now, whenever you have this dipole moment, so there is some positive and negative type of charges on opposite faces or opposite layers, then the fresh ions will, which are say positively charged ions, will then come closer to the negatively charged faces, and the negatively charged ions will come closer to the positively charged faces. So, if you look at zinc oxide, for example, the Woodside structure of zinc oxide, in that the 002 faces are polar faces, that means they have some polarity, and the opposite phases 002 faces, two opposing 002 faces have zinc 2 plus ions on the surface and oxide 2 minus surface on the ions on the other surface. So, one surface of the 002 is positive and the opposite 002 surface or face is negative. Now, so the next zinc 2 plus ion will come closer to the 002 phase, which is negative, that is, which is having oxide ion terminating on the surfaces, and this way the process is continued by oriented attachment led by this permanent dipole moment, which are present in this polar systems. In zinc sulphide or zinc blende structure, which has the zinc blende structure, the 1-1-1 faces are polar. So, in this case opposite 1-1-1 layers will have either positive or negative charges, and accordingly the subsequent ions, say the sulphide ions, will come and attach to the surface which has the positive charge, that means which is terminated by zinc 2 plus ions, and similarly the zinc 2 plus ions will come and attach to the surface which is terminated by sulphide ions, and this way the crystal growth will take place in a very oriented manner, and you will have this nanorod formation. So, the dipole moment along the 002 phase of zinc oxide and the 1-1-1 phase of zinc sulphide is important for the growth of nanorods in this system. Now, to give you an example that the microemulsion is important for the nanorod formation, here we show on the left panel a nanorod of dimensions maybe few, the length is of several microns, maybe 4 microns or 5 microns, and the diameter may be around 300-400 nanometers or maybe larger, and this nanocrystal is of or submicron sized crystal is of zinc manganese oxalate, which has been synthesized using reverse micelles, that is using microemulsions. On the right side, we have used the same conditions for making the same compound using the co-precipitation method, where we do not have any surfactants or microemulsion. And as you see, this microemulsion process containing a cationic surfactant gives a nanorod kind morphology, whereas in this case, where we have not used any surfactants or microemulsions, you can see that there are no rods or anisotropic structures. They are more or less spherical agglomerated particles of zinc manganese oxalate. If you take the X-ray diffraction of both of them, they will have the same X-ray diffraction, telling you that in both the cases the product is the same. However, the morphology is very much dependent on the methodology, how you have obtained them. So, if you use reverse Meissler method, you get these rod shape structure. If you do not use reverse Meissler method, no microemulsion, then you get these sphere like structures. Of course, these materials are important and they belong to a structure called the spinel structure and are useful for photocatalytic applications. So, this is one example, but there are many examples we can show where the metal oxalates synthesized using microemulsions show anisotropic or rod like structures compared to spherical or irregular structures if you do not use the microemulsions containing a cationic surfactant. So, this is another example where we have made manganese oxalate rod like structures using microemulsions with CTAB as the surfactant, and you see, as explained earlier, we have rods which have diameter of around 70-80 nanometers and lengths of say several microns. And if you decompose this manganese oxalate rods under some condition, that is, you can heat this in air or oxygen or nitrogen, depending on the environment in which you decompose these manganese oxalate rods, you will get different oxide nanoparticles like MnO, manganese oxide, manganese 2 oxygen 3 and Mn3O4. All these 3 oxides are of size in the nanometer dimensions. Some are smaller, say 20-30 nanometers, and some are larger, say in Mn2O3 we get sizes around 50 to 70 nanometers, and in Mn3O4 we can have sizes around 100 to 200 nanometers. So, you can get different oxide materials under different conditions of synthesis, like the decomposition temperatures and the environment in which you are decomposing is important. And if you have more oxygen in the environment, you will get more oxidized species of manganese. Manganese here is divalent, and here manganese has an average oxidation state of 3/2, right. Here it is 2 and here it is you have 6 charges for oxygen, and manganese here is trivalent. So, here it is divalent and here it is trivalent, and here it is a mixture of divalent and trivalent. So, depending on the conditions, so the more the oxidized the species, you need higher the partial pressure of oxygen during decomposition. All these oxides are very important because nanostructured manganese oxides have lot of applications in battery materials. Now, let us give you an example how the solvent affects the shape and size of these nanostructures. So, solvent molecules interact with the surfactant tail, because the surfactant tail is hydrophobic and the solvent is a non-aqueous medium in these cases. So, the surfactant tail will interact with the hydrophobic solvent, and that will affect the exchange of the ions between the two micelles during interactions. Now, so for example, you choose the system of the synthesis of nickel oxalate using a C-tab surfactant, and then we compare different solvents, different hydrocarbons, hexane, cyclohexane and isooctane. Now, all these three are hydrophobic and will interact with the surfactant tail. Of course, the hydrophobicity will vary with the different kind of solvent. Now, if you have a bulky solvent, it cannot penetrate the surfactant tails at the interface. At the interface of water and oil, that is water and the non-aqueous medium, the surfactant will be aggregated, and the bulky solvent which is outside this interface cannot penetrate the surfactant tails, and hence the interface becomes more fluid, and whenever the interface becomes more fluid, then that enhances intermicellar exchange. In other words, whenever you have bulky solvent molecules, you have more fluidity at the interface and you have enhanced intermicellar exchange. And when you have enhanced intermicellar exchange, the particle size will be larger, and hence particle size is larger when the solvent is bulky. So, this what we discussed we can see in experiments. So, if you choose three solvents, hexane, cyclohexane and isooctane, the bulkiness increases like this. So, hexane has the least bulky and isooctane is more bulky, it has 8 carbon, this is 6 carbons, and you can find out that the highest aspect ratio you obtain, the aspect ratio is the when you divide the length with the diameter, you get the aspect ratio. So, the aspect ratio becomes larger as the solvent becomes more larger or bulkier. So, hexane is the smallest in size and the aspect ratio is 5:1, whereas cyclohexane and isooctane the aspect ratio increases to 6:1 to 11:1. So, you can enhance the aspect ratio and the size as you increase the bulkiness of the solvent. Now, you can see the same thing in another example. So, this was the example of nickel oxalate, when you have one microemulsion having nickel and the other microemulsion having oxalate, and then you can take another example where you have the solvent is isooctane and N-octane, you are comparing two solvents and you are keeping the other things constant. So, you are taking the same surfactant C-tab and you are taking in one solution copper and in another solution oxalate ions, and you are mixing them and intermicellar exchange occurs and copper oxalate hydrate forms as crystals, and in isooctane you see much larger particles like this. In N-octane you see much lesser, the diameter here is much larger, the aspect ratio is larger here, and these kind of effects in controlling the morphology can be seen in all such nanostructured materials. Of course, if you decompose these copper oxalates at around 400-500 degree centigrade, you get copper oxide, and the copper oxide that you get from this is different in size, is 25 to 30 nanometers, while the copper oxide that you get from normal octane has the size of 80 to 90 nanometers, and that brings about difference in their magnetic properties. So, this is an example how the size can be controlled through the oxalate precursors, and that difference in size 25 nanometers and 80 nanometers will bring about a difference in the magnetization, which is plotted on the y axis compared to the magnetization in the other case, and the difference in these two is just the size of the particles. So, you see that there is some transition here around 80 Kelvin, and that transition in this these nanoparticles is around 190 Kelvin. So, this change in the particle size brings about the change in the magnetization in copper oxide. Now, you can see the same thing, the solvent is controlling the morphology. So, you are changing from cyclohexane, that is the solvent here, to hexane, to isooctane, right, and in this case we have changed from butanol, which is a co-surfactant, to pentanol, which is a bigger co-surfactant. So, the top two show you change in the dimensions of the nanostructured materials when you change the solvent, and the bottom two slides show you what happens to the morphology when you change the co-surfactant. The co-surfactant normally is an alcohol. So, in this case we have taken butanol and in this case pentanol. So, we have increased the length of the hydrocarbon chain from 4 carbon to 5 carbon, which brings about some changes in the morphology. So, you can bring about changes in the morphology from the changing the solvent, the surfactant as we discussed earlier, and the co-surfactant. If you want to monitor the effect of one parameter, we keep all the others constant. For example, keep the surfactant same like CTAB, keep the solvent same like isooctane, and then change the co-surfactant in this case. In this case, you keep the co-surfactant same, but the solvent has been changed, and so you see the effect of the solvent on the aspect ratio and the size of the nanorods of copper oxalate. This is another case where the surfactant we have changed from cationic surfactant. We always get rods, as we discussed in the previous slides. If you change the cationic surfactant to TX100, this is called Triton X100, it is a neutral surfactant of some molecular weight, some size, we get spherical particles, not rods like you get in cationic surfactants. This is nickel oxalate dihydrate. In all the cases, you will get same X-ray diffraction pattern telling you all of them are nickel oxalate dihydrates, but when you look at them, some of them are rod like, some of them are spherical particles, and some of them have cube like shapes, and that is because you have changed the surfactants from CTAB, which is a cationic surfactant, to a neutral surfactant like TX100 to another neutral surfactant of a different size, which is tergitol, and you get different shapes of these oxalates. And if you decompose them, you of course get nickel oxides of different sized particles. So, you have 25 nanometer particles, 20 nanometer particles, and 10 nanometer particles based on the precursor that you use, and the precursor size you have controlled using the different surfactants in each case. So, this is another example of controlling the size and shape using surfactants. Earlier we showed nickel oxalate, this is copper oxalate, where you have changing the surfactant from CTAB, which is a cationic surfactant, to AOT, which is an anionic surfactant, and then this is again a cationic, but it has a restricted rotation because you have a pyridinium group here. So, this is cetyl pyridinium bromide, whereas this is cetyl trimethyl alkyl bromide, and you see the shape of these particles are not so rod like compared here, they are more spherical. However, if you use another surfactant like TTAB, so of a different dimensions, different chain length, you get again rod like structures. So, the surfactant has a very important role in controlling the shape of these particles and the size of these particles. So, this is more or less what we discussed already. If you have a C16 carbon, C14 carbon, this is a larger tail hydrocarbon chain, the smaller hydrocarbon chain, more compact packing, there is a smaller aspect ratio. If you have CPB, which is a pyridinium ion, you have a restricted rotation and you get smaller aspect ratio. So, these numbers we have tabulated. When you have C tab or another surfactant T tab, so you are varying the surfactant, keeping the co-surfactant same, the solvent is the same, the W naught parameter is the same. So, only variation is in the surfactant and you get variation in the average size and morphology or the aspect ratio, which is the ratio of the length is to breadth, and that changes like going from 3.7:1 to 2.7:1 to 1.5:1 by changing the dimensions of the surfactant. And this is the surface charge, the charge of the surfactant. So, you have positive charge in C tab and you have neutral charge in TX100 and tergitol, which are non-ionic, and here you see isotropic growth, whereas in the cationic surfactant you see more anisotropic growth. So, they are more the aspect ratio is nearly 1, they are cubic in nature, whereas the aspect ratio is here 3:1. So, the co-surfactants I already discussed. Co-surfactants have short length short chain alcohols or amines. They help the surfactant to lower the interfacial tension and they lead to higher fluidity of the interfacial film and increase in intermicellar exchange rate. So, the co-surfactants basically like we have used butanol or pentanol etc., help in decreasing the interfacial energy between the water medium and the non-aqueous medium, the solvent which we are taking, which may be isooctane or heptane etc. Now, so this role of co-surfactant we can see more in detail. So, here you have butanol, pentanol, hexanol and octanol. So, you are varying everything else is same, you have C tab as surfactant in all these cases, only the co-surfactant is varying and you can see a variation in the diameter and length of these particles. So, if you go from butanol to pentanol to hexanol, you see the aspect ratio is changing, and then beyond hexagonal the aspect ratio comes back, it becomes cubes. So, there is an optimal chain length of the co-surfactant and it appears to be 6 carbon is an optimal size, and we have seen that if you increase beyond hexanol, then you get aspect ratio of starting to become less, and then they become in octanol and decanol, which are the very large chain co-surfactant 8 carbon and 10 carbon, they become more uniform and nanocubes and nanoparticles start forming. So, you start with 5 carbon, 6 carbon, 7 carbon, 8 carbon and 10 carbon, and up till say 6 or 7 you see the anisotropy, and beyond that you see they becomes more uniform particles. And this we have tried to explain that beyond C6 the carbon chain in the co-surfactant starts interacting with the surfactant tails, because the co-surfactant tails are hydrophobic and the surfactant tails are also hydrophobic, and they start interacting with each other, and hence it affects the intermicellar exchange and it actually prevents decreases the intermicellar exchange, and hence it reduces the size of the particles which are formed. So, this is already what we discussed in heptanol and decanol. We can see that the morphology changes and up till 6 carbons in the co-surfactant the size of the particles increases. So, to compare all of them, we have made this table where we are seeing variation of solvent, isooctane, cyclohexane and hexane, and you can see the average diameter and the average length and the aspect ratio and the morphology. is changing depending on the type of solvent, and we have explained that as the solvent bulkiness is decreasing or increasing. In this case, cyclohexane is greater than isooctane and is greater than normal hexane. So, the growth rate increases and the aspect ratio decreases, and this we already explained, because bulky molecules will give a more fluid interface because they cannot interpenetrate, and hence intermicellar exchange will increase and the size of the particles and aspect ratio will increase. Now, in the variation of co-surfactants, we saw that till C6 or C7 the chain length will increase, after which it will start decreasing. So, this is a kind of example that where we are showing what happens when you change the water to surfactant ratio, which is the W naught parameter. So, if you keep the surfactant, the solvent and co-surfactant same in all these 4 cases, the surfactant and the solvent are not changed. Only thing which is changed is the W naught parameter. So, the W naught parameter is here, which is the water is to surfactant ratio is 9, and here it is 11, and then here it is 12 and 15. And so, the W naught parameter is changing and the shape of these rods are changing, and this is an example of copper oxalate monohydrate. You have taken 1 microemulsion of copper ions, another microemulsion of oxalate ions with this surfactant CTAB with isooctane as the solvent and 1 butanol as the co-surfactant with varying W naught parameter, and you are getting different aspect ratios. So, what we find is as the W naught parameter is increasing, the aspect ratio is decreasing from 3.75:1 to 2.5:1. So, this is another case of W naught 18. So, this was 15 and this is 18 and it further decreases. So, more or less if you plot the aspect ratio versus the W naught parameter, it appears to decrease as a function of W naught. So, larger the W naught, the aspect ratio is smaller, and this is again shown as a variation of W naught, and the aspect ratio is shown here. It decreases more or less with some fluctuation here as the function of W naught parameter. Now, you can further see this in the case of another surfactant, that was with CTAB. If you use another surfactant like Triton X100 and you vary the W naught parameter from 11, 14 to 16. So, in this case what happens, you are changing the W naught parameter, the size of the particle is increasing because you have more water, more crystallization, the reverse micelles are larger in size and you get the size of the particle increases. So, this is for case where you have taken a neutral surfactant, where you get uniform particles, cube like particles and not rod like particles. In the earlier case we had taken CTAB as the surfactant, which gives rise to anisotropic structures, and in this anisotropic structures as we increase W naught, the aspect ratio continues to decrease, which is in a way tells you that the size of the particle, the spherical particles or the cubic type of particles will increase as the W naught parameter increases, whereas the anisotropy will decrease as the W naught parameter will increase. So, in a more constrained reactor, in a more constrained reverse micelle, the anisotropy is higher. So, this is another example of how using different W naught parameters. This is for copper nanocrystals. We were showing in the earlier slides copper oxalate or nickel oxalate, these kind of nanostructures. This is a slide where you see just copper nanocrystals with varying W naught, and you see different types of size and shape. So, you have spheres for W 32, and you have these kind of particles when you have W naught is equal to 28, and when you have W naught equal to between 9 and 10, you seem to get this kind of rod and particle type of mixtures for copper. And when you are in this range, which is around 6, 7, W naught is equal to 6 or 7, you get again more anisotropic structures and spheres. So, this is a study on copper nanocrystals reported earlier. Now, we also see that the role of oxidation state also plays a part, because if you see that whatever metal oxalate rods we discussed, in that always we had metal in the divalent oxidation state, like cobalt 2 plus, nickel 2 plus reacting with oxalate ion in the microemulsions gives you rods with CTAB as a surfactant, cationic surfactant. However, if you choose the same system like CTAB based cationic surfactant and study the synthesis of cerium oxalate or zirconium oxalate, we get particles and not rods, although we are using CTAB as a surfactant, which is a cationic surfactant. So, it suggests that the oxidation state is important, because cerium here is not divalent, it is trivalent, and zirconium here is tetravalent and not divalent. So, it appears that the 1:1 ratio oxalate ion is negative, and the metal ion, if it is positive and they have same charge of course opposite, then it forms anisotropic nanorods in a CTAB based microemulsions, whereas when the oxidation state is larger, say 3 or 4, then they are giving rise to spherical particles of zirconium, cerium oxalate and zirconium oxalate. Of course, they again can be decomposed to give you zirconia or ceria depending on the conditions, and in this case we stabilize a tetragonal ZrO2 phase, which normally is stable only under certain conditions. So, you can make metastable phases using the microemulsion process. You can choose, instead of oxalate, you can choose succinate, and then what we find, we do not get the rods, we are getting particles. So, the anion is also important. In all the earlier cases, we chose oxalates as the anion, and we got rods in the presence of CTAB. Here we see, although we have chosen CTAB as the surfactant, everything else is the same, except we have changed the succinate from the oxalate, we get particles and not rods. So, that means the ligand is also very important, one of the important parameters of the formation of anisotropic structures. Here we see that this is copper succinate. In this case, depending on the ligand, we see we can get crystalline anisotropic structures under certain cases, and you can change it to amorphous structures, and that amorphous structure can again give rise to particles like this, and on heating can give rise to the oxides. So, this is iron succinate, where it was the trivalent iron was used. So, trivalent iron was not giving any rods, whereas divalent copper gave us anisotropic rods with succinate ion also, and some we can transform them to at room temperature. They are crystalline rods, as you can see from the transmission electron microscope, and if you heat it, it becomes amorphous, the crystallinity disappears, and if you look carefully you can see these particles, and these particles when under a high resolution can show you these lattice fringes, and on decomposition they will give you copper oxide like they can be obtained from copper oxalate. So, again we show you the same copper succinate dihydrate synthesized using CTAB in the absence of reverse micelles at room temperature, and they are slightly different. And if you use the reverse micelles, you are getting these crystalline rods, whereas you can change the morphology of these rods by choosing whether you want to do in reverse micelles or in the absence of reverse micelles. So, by this we come to an end today of the various examples of synthesizing nanostructured materials using microemulsion. So, I hope you have learned some basics of microemulsions and the technique to make nanostructured materials and how to control the shape and size of these nanostructured materials using microemulsions. So, we meet next time for a new methodology. Till then, thank you and goodbye.